Hello everyone, I'm Mohammad Hani from Data Science Dojo, and today we will be diving into vector databases explained. It's a really powerful tool, vector databases, that you can use for your personal projects or as well as your enterprise-wide solutions. So let's get started. First of all, let's have an overview of the session. Firstly, we will understand the evolution of data and the types of data and storage that we have to understand the problem better. Second of all, we will start, we will have an introduction of vector embeddings and their importance. Thirdly, where those vector embeddings are going to be stored is vector databases and how similarity metrics are computed to to find similarity between those embeddings. And lastly, we will be ending it with the live project to get started with vector embeddings, and for this we will be using Pinecone. So let's get started. Your manager has assigned you a task where you are provided with a 200-page book, and you have to extract information from a list of topics. The list of topics has been provided, and on the basis of that information, you have to write a report as well as provide references. So let's think how we might actually be able to sort out this problem. The first solution for this would be that you go page by page, extracting the list of topics and the relevant information along with it. And by skimming through all of those 200 pages, you'll be able to extract all of this information. Once you have extracted the information, you'll write the report and provide references. But it seems like a very uh, it seems like a boring task, doesn't it? So you think a little bit and you realize that a book has two things that can actually help you with this. One is a table of contents, which is available at the start of a book. And secondly, we have the index, which is provided at the end of the book. So you can actually go through the table of contents, extract the relevant topics and their pages. You go to those pages and extract the relevant information. Similarly, based on these list of topics, you can extract keywords, use those keywords to extract page numbers from the index, and use that information to write the report. Seems pretty simple, right? But when you actually open that book, you do not have any table of contents. You do not have an index either. It's just purely a poorly written document. So what can we do to resolve this kind of a problem? We'll be looking at it at the end through the live project. So for now, let's name this problem as the document search problem. Pretty simple, right? Before we dive into any sort of problem dealing with data, we need to understand the types of data that we're dealing with. We have our unstructured data, which does not have any predefined data model. It could be PDFs, images, audios, movies, even the transcript of this session could be considered an unstructured data. The reason why it's called unstructured is that it does not contain a data model. On the other hand, we have our structured data, which are usually our SQL databases such as MySQL or SQL Server. The reason why these are called structured is that they already have a predefined data model. In between these two, we have a semi-structured data, which could be your comma separated values, JSON objects, or your NoSQL databases. So let's think about it for a few seconds, that the problem that we are trying to solve, the document search problem, the data inside that problem, what sort of data is it? Is it unstructured? Is it structured? So yes, it's unstructured data that we're trying to deal with. What usually happens in real life scenarios is that we start with a structured format of data, But as time goes on, we move towards a more unstructured format. So let's have a real life example of what actually looks like this. So you start a company, you have a few business proposals, you have a few documents that you can just store in the Word doc. You have a few employees, all of their details could be stored in an Excel file. And you can manage that, and that would be enough. It would seem enough, right? But you know that as time goes on, it's going to get more and more complex. So for that, you will need to introduce some sort of a directory structure, like a folder structure or a hierarchy to store that information, so that whenever you need to extract relevant information, you're able to navigate to a particular folder and open those folders to get the details. But still, as time goes on, you're going to be left with a lot of Excel files and a lot of Word documents. And it's going to be very complicated, since some of these Excel files are going to be having multiple versions. Similarly, with the doc files, you're going to be having a lot of versions, and it's going to get messy. To resolve this, you can introduce an enterprise content management. Now, this is some sort of a problem that you're going to deal with in real life scenarios. That you're going to have a very structured sort of data, but it's going to get more and more structured. So it's key that you understand what sort of scale, what sort of scalability are you looking for, and how sustainable is the solution that you are trying to figure out. Even in the enterprise content management solution, you might not be able to find relevant files when you perform a keyword search using it. So that's where the importance of having a custom search solution comes in. That you want to extract relevant information. In the previous example that we covered, we were talking about extracting text from a list of topics. The document search problem, it was basically a text-based problem. But here, you could also have a file-based problem. So you'll have to create some sort of solution for files instead of those list of topics or the table of contents. You will have to create some sort of a structure for these files. So let's take an idea what vector embeddings are and how can they improve our lives with this problem. Vector embeddings are simply numerical representations of data. And if I had to provide an example of how we can convert this data into vector embeddings, I'll share it with you just now. But before that, we need to understand that data has multiple types. It could be text, it could be files, it could be images. And when we are converting this into vector embeddings, we can convert any sort of data into vector embeddings. So let's say I have a sentence. I have 5 apples of weight 200, 250, 130, 300 grams, and 230 grams. And I want to convert this into some sort of an information that computer is going to be able to understand easily. One thing that I can do is I can just create a list of numbers, but notice there's a particular order in the way that this list is arranged and what this list could actually mean. I'll give you guys a few seconds to figure it out and then reveal the solution. So the list that we just converted was actually a weight vector, right? So one single position, so a position of this number represents which apple are you talking about. The value of this number itself is going to be the weight of this apple, and the entire vector is represented in grams, right? Another thing that we can deduce from this is that the sentence was converted into a vector with 5 dimensions, since we're talking about 5 values, which are 5 apples. Similarly, we could have a volume vector as well. Let's say the sentence also contained the volumes of each of those five apples. We can convert a volume vector as well. And so we have a weight vector, which is represented in grams, and we have a volume vector, which is represented in cubic centimeters. Now, we have an example. We have an idea of how we can actually convert data into vectors, but how are we going to be able to compare them? Is something that you might be thinking. That's where embeddings come in. Embeddings generally mean putting something into something else. But in terms of computer science, it's going to help computers understand relationships between objects. So suppose that you had individual vectors for each of these apples instead of the uh, whole weight vectors and the volume vectors. How would they look like? How would a single apple provided from this in this given information, using this given information, how would an apple vector look like? It would look something like 200 comma 235, where the first position would be the weight of that apple, the second position would be the volume of that apple. And if we had to like visualize those vectors of apples, we could do it something like this, where we can plot volume at x-axis and weight on the y-axis. So this is how you can actually visualize vectors, and we'll look at how we can actually compare them later in the series. So before going on with the technical details, let's have another example of the overall view of how vector search and how vector embeddings can actually help us. Suppose you have a news article website. This website contains thousands of news articles, and every day you have multiple users coming in. Now, at the end of each news article, you want the user to be shown the most similar articles at the end of their read, right? So at the end of the read, they're shown the article which is most similar to the one that they're currently reading, right? And to solve this, what might be the way? What might be our very feasible solution? One solution would be that we work on keywords. We extract keywords of all of those news articles, and we save those keywords. Whenever a user lands on a particular news blog or a news article, those that article's keywords are going to be searched. We are going to perform a keyword search across the entire database and find the most similar news articles based on the keyword search. But if you think about it, it's going to be it's going to take a lot of time, and it's going to miss a few things as well. First thing that it's going to do is it's going to perform an entire keyword search, which is going to take a lot of time because we are comparing strings, we're not comparing numbers. Secondly, it's going to miss out on context. Maybe a particular keyword is being used in an opposite context as to what the user is reading. Similarly, it could miss out on nuances, maybe something like pronouns. It would the keyword search would not be able to understand those things and those complexities. So where so in this case, context is the main problem that is being lost, and we want the user to read the most similar articles at the end, right? So one way you could perform this using vector search would be that you transform all of those news articles into vector representations. So let's say one block here represents a vector representation of a single article, right? And we have a lot of vector embeddings for each of those um, news articles. Pretty simple, right? Next, whenever a user lands on a particular article, it's going to be treated as a user query. So we are going to treat it as the user wants something similar to this particular article, which they are currently reading. The next thing it's going to do is it's going to perform a similarity search. Notice something in between the similar ones that it found and the one that it then the one that the user is currently reading. I'll give you a few seconds to notice the similarities between these three. So some of you might have guessed correctly that the first indices, the first positions, they're all divisible by 3. The last ones, they're all divisible by 4. Then we have this similarity between 1 and 3, where 8 and 4 both are divisible by 4. 5 and 5 are both divisible by 5. So it's not some complicated math. It's a very simple architecture, like it's a very simple way of comparing. And it generally goes something like this. It's not exactly like this. This is just an example to give you guys a visual understanding of how vector search is carried out. So once you are able to find the similar ones, you can just display those two articles at the end. Seems pretty simple, right? Now, we were talking about very simple scenarios and simple examples, but when you're talking about real world embeddings, this is something what it's going to look like. Now, don't worry. Embeddings are not something that you will have to manually create or write program for. In this scenario, in this session, we are going to be using an embedding model for creating embeddings, and similarly for your own personal projects as well as enterprise solutions, you will be opting for some sort of an embedding model. They're usually AI models that can help you create vector embeddings. If I had to visualize a few question answer pairs, this is something that it would look like. The example is taken from Cohere semantic search, and you guys can actually go play around with the Cohere playground, which our team will be sharing with at the end of the session. So we have a few question answer pairs, and look how similar they are going to be visually. Where was the last World Cup? The last World Cup was in Qatar. What color is the sky? The sky is blue. This is just a visual representation of going through and grinding through all of those hard numbers to get an idea of what similarity between vectors would look like. So now that we've covered vector embeddings, let's look at vector databases and how they're actually going to help us with finding out similarities. We have a few popular vector databases here. The first categorization is that there are a few dedicated vector databases which were created specifically for the task of vector search. Similarly, we have the second category is databases that support vector search. These could be your SQL databases or your NoSQL databases, but they do support vector search as well. Another way of categorizing these vector databases is the open source databases and the ones that are available for enterprise. Today we'll be covering Pinecone, but don't worry, we'll be using the free version of Pinecone, so everyone will be able to experiment with this. So let's look at the similarity matrix and how similarities are calculated between these vectors. First of all, we have our Euclidean distance, which is going to cater out both magnitudes and direction. Similarly, we have dot product similarity at the third one, which is also going to cater out both magnitudes and direction of the vector. While cosine similarity is something that is only going to calculate on the basis of direction of those vectors. So the first metric that we have is Euclidean distance. I'll give you guys a few seconds to read this slide out, so don't worry. Um, if we had to visualize Euclidean distance for two-dimensional vectors, this is how it would look like. So if vector A and vector B only had two dimensions, and we had to visualize it, this is how it would look like. And for an n-dimensional vectors, this is how the equation for Euclidean distance would look like. So we have vector A with their first dimension, vector B with their first dimension. Similarly, vector A and vector B, we're just going to subtract these, perform a square root, add them up, add them up, and after adding these, we'll have a square root, which will be our Euclidean distance. Now, understanding Euclidean distance is very simple. That is that when the distance is very small, the values of each coordinate are very close. So if the Euclidean distance that you calculated for two vectors is very small, that means that these vectors are very similar. If the Euclidean distance is very large, that means they are not very similar. Pretty simple, right? I'll give you guys a few seconds to read out this equation before going ahead. Similarly, we have our dot product similarity, where we're simply going to perform a dot product between the two vectors. So it could be any n-dimensional vectors, and we will perform a dot product. So it will be something, so it will look like something like A1 multiplied by B1, A2 multiplied by B2, A3 multiplied by B3, and just add them up. And this is what we'll be getting for the dot product. Similarly, we could also visualize it as the product of their magnitudes and cosine of the angle between these two. To understand dot product similarity, here's the explanation. If vectors A and B are pointing in the same direction as each other, the dot product of A and B will be larger. So similarly, to simplify it, this technical detail is that if the dot product is larger, they are not very similar. While if the dot product is not large, they are very similar. Lastly, we're going to cover cosine similarity. Now, cosine similarity is different from the previous two since it's only going to consider the direction of these vectors. It's not going to consider any sort of magnitude or distance. So here's the equation for the cosine similarity, which we can also access from Pinecone's official documentation. And lastly, if we had to understand how cosine similarity works, it's going to vary between -1 and 1. -1 is where the two vectors are going to be completely dissimilar, or they're going to be in opposite meaning. When we get a cosine similarity of 1, it means these vectors are as close as they possibly can, or maybe perfect similarity. When we are talking about cosine similarity of 0, although this means that they are orthogonal, they do not have any kind of similarity in between. So now that we have an idea of how the metrics are computed, let's look at a real world example where vector databases are used. In LLM applications, there's this particular architecture that is very common, which is called the RAG architecture. And inside this RAG architecture, which is our retrieval augmented generation, vector databases are very popularly used. And in which step they're being used? You guessed it right. It's in the step C. So first of all, there's a query that goes inside, that goes to the vector database, and all the relevant information with the enhanced context is retrieved. That retrieved context, along with the prompt and the query, can be sent to your OpenAI model. And once you send all of these, you will be able to get a customized answer from your LLM. I'm sorry for using the word OpenAI. You can use any LLM for this architecture. And how the vector database is going to like retrieve information? It's going to have stored knowledge bases or knowledge sources, and all of these are going to contain vector embeddings. So to give you an overview, whenever a query arrives, the vector embeddings, which are very similar to those which are very similar to that query, those vector embeddings are going to be returned. Those vector embeddings are going to be embeddings created from original knowledge sources. So you can retrieve all of the context related to a particular query, pass it on to an LLM, and retrieve your customized answer. So we've mostly covered the theoretical part. So, and before diving into the technical code, let's go through the project overview. First thing that we're going to do with solving the document search problem is, okay, I'm hopefully you guys remember the document search problem that we discussed in the first few minutes of the session. We're going to be solving that. So first of all, we're going to load the document. Next, we're going to create chunks of that document. The reason why we are creating chunks is whenever we want to create embeddings using an embedding model, there is usually a token size limit. To cater to that token size limit, we have to perform some sort of chunking. Now, there are multiple strategies for chunking, such as context aware chunking, and we're going to be using one of those. But to have a very simple explanation for chunking is, let's say you have a 200-page document, and the embedding model cannot create the embedding for the entire file, like the entire file. So what you're going to do is, what you could do is, you can chunk them one by one, like page by page, and each page will have its own embedding, and you can just reference those embeddings. So after we are done with chunking, we're going to be creating embeddings, store these embeddings, and then run a query upon these. After when we run this query, we're going to get customized. We're going to be completed with our customized search solution. So let's get started with the code. So I'm going to pause for a few seconds so that you guys can note these packages down that we are going to be using. Don't worry, we will be providing you a GitHub link for this code so that you are able to get started with your own developing your own search solution. First of all, we're going to use LangChain. LangChain is a wrapper around the Pinecone and multiple LLM development modules. The reason we're using this is it's going to create a lot of ease for us, and it's something really worth looking into if you're into LLM app development. Secondly, we're going to use Pinecone for accessing Pinecone. Thirdly, we're going to be using PyPDF to access the PDF file that we have. We'll be using OpenAI for creating embeddings. And lastly, TikToken is actually kind of a dependency for LangChain. It's going to help you find out the number of tokens that you're using. To understand tokens, remember that we talked that there was a particular limit when you're trying to use an embedding model. Those that limit is based on tokens, not on characters, not on words, but on tokens. Um, Another thing that you might want to note down is the version of the line chain that I'm currently using. So this is how, so like this code will be dependent on this particular version, and it might, so that you do not face any difficulties when you're trying it out yourself. So let's start with the imports. We will be creating our local environment, loading our local environment, and importing the relevant all the relevant packages and libraries. Next, we have our Pinecone API key, which you can get from your environment. So before we get started with the API key and everything, let me give you guys an overview of what Pinecone might actually look like. So when you log in, you're going to see a screen like this. When you log into Pinecone, you're going to see a screen like this, and you might be tempted to use this option, but if you're trying to create like if you're trying to understand the vector databases, I would not recommend using this. You can just go through, create an index, add a name for your index, add dimensions which you can select using these models. So let's say I create ADA2, set configuration, and I will say test project. And since we're using the free tier, we can only create a single index. So I'm using a different account for creating this index, right? So you're going to have created an index, and secondly, you're going to have an API key. You can just copy this API key and paste it into your project and hard code it, or you can use in a virtual environment, which is actually a good practice. And you're going to have a lot of important information. All of these, some of these are we're not going to use, some of these we are going to use. So just get an idea of what this is. And I have already created, an index for this session. So this is how it's going to look like. So we have cosine similarity as our metric for comparison. We have our pod type. We have our host, our environment, and all of the necessary details that we would need, such as the API key. So I would like to repeat once more, when you have a free account, you can only create a single index in Pinecone. So that's just that, that's just a detail that you need to remember. So we import the Pinecone key, and next we are going to get started with a little bit of LangChain. File PDF directory loader is something that LangChain provides. So um, I have this directory called PDS, in which we have our sales management book, which is of 200 pages. You can see here, it's a 200-page book, and it has a table of contents. But the thing is, the problem with this is that the table of contents are for different sections. So like each section has its own table of contents. There's no overall table of contents. So anyways, let's go back to the code. We'll load the PDF and we'll start a data loader. Secondly, if we need to get an idea of what the data actually looks like, this is how it's going to look like. Using the PyPDF, it just made it a lot simpler. We have chunked down the entire document page by page. Pretty cool, right? And at the end of this, we're going to get in metadata the page numbers as well. So it's a cool wrapper that you guys can use. And if I wanted to get an idea of how much the data we have 202 documents, so we know it's page by page. Secondly, we are going to recursively character text split. The reason for this is that we want to have an idea of the accurate chunk size. Today, for this session, we are going to be using a chunk size of 480 with a chunk overlap of 20. The reason for chunk overlap is so that we do not lose context where the words are just split in between, like in between sentence, two different words are being split and we do not have a chunk overlap, we're going to have a problem with context. So there's that, and we're going to provide a separator list as well. The reason for this is that you can just opt not to do this, but there's a problem that's pointed out in the LangChain documentation that says that if you are going to use the default separator list, it can cause words to split between. So like if I have a word bad, it could just split in between like this. And you would be left with bar and D, and that would make no sense at all. So anyways, let's start with the character text split. So we have each chunk now is not of a single page. Each chunk is of 480 tokens. The general rule of thumb when like identifying tokens is that 4 characters is equal to 1 token. It's just a general rule. It's not something that is enforced, but you can use this to estimate the number of tokens you have in your data. Next, we are going to split these and let's take a look at what the chunks look like. So now we have even smaller chunks, but each chunk does not refer to a single page. So you have page 1 chunk here, and you have another chunk which corresponds to page 1 here, and you have another chunk which corresponds to page 1 here. So yes, we're just splitting it down to more details. It's just that like it's a design decision that you can take to the number of detail or to the number of summary that you want these chunks to be. So if we get an idea, we have 882 chunks based on those 202 pages. Next, we're going to get started with creating embeddings. Here today, I'm using Azure OpenAI embeddings instead of OpenAI embeddings. So it's going to be a little different. I'm going to import another package from LangChain for Azure OpenAI embeddings and create my embedding model. For those of you who will be using the simple OpenAI embeddings, you can use this piece of code where you will be adding your keys, which usually start with SK and hyphen, and your environment, and add those keys into your environment, and you will be good to go. Once you have this embedding like this embedding object, you can use this to create embeddings. Let me show you what embeddings actually look like. So as we discussed previously, it's not very simple at all when we have like 1500 dimensions now for the ADA model of Azure OpenAI. So this is how an embedding is going to look like. If we want to have an idea and just cross check, yes, we have 1536 dimensions. And if you want to check here, we have set the index for 1536 dimensions. Pretty cool. So let's get started with Pinecone. I'll import Pinecone, import my keys, get started with the objects. I've added my host ID as well as my index name, and I will be initializing the index object. Next, we have to create embeddings for each of those sections. Previously, what we did here, I just showed you guys an example of how you can create an embedding using the hello string. So this thing is just an embedding of this particular string, hello. When we are going to create embeddings for all of those 800 chunks, we will have to like iterate through the entire thing. So I have my index object, right? So using this index object, I'm going to run this piece of code. Another option that you can take is using the doc search method, which is usually provided in other documentations as well, to perform your like document search. But here I'm going to be using a little different approach. So let's start from inside out. We create our vector, which contains an ID, value, which will contain the page content, and metadata, which will contain all of the extra details related to our chunks. Next, what we're going to do is we're going to upsert this into this index, this vector, and the namespace is going to be real. Where did the namespace come from? The namespace comes from here. And what since we want to like iterate through the text chunks, we want to create index and text pairs. So we take our text chunks that we created previously, we create pairs. It's going to look something like 0, comma, and ABC. It's going to look something like this. This is how it's going to look like these pairs are going to look like, and we'll iterate over all of those chunks. So a single chunk is created. So from a single chunk, we create a single vector, we upsert this into the index, and we're good to go. So I'm not going to be running this one because it's going to take a lot of time. So I've loaded this index previously, and let's just get an idea of what the index actually looks like. So we have 1536 dimensions, and we have 800 chunks, which are our number of vectors as well. So one chunk corresponds to one vector. So let's suppose in the document search problem, you were provided with these three topics: the national sales meeting, SMBO process, signs that justify it, territory revision. So if I want to, I will be performing a query, a vector search on this index of Pinecone that we just created. So first of all, I will have to convert this query into an embedding, ask this embedding from the index, and the result will also be an embedding. So if the result is going to be embedding, how are we going to extract relevant information? Well, we're going to be using our original text chunks for this. So if I had to show you, so before that, I converted this into an embedding, and we're going to extract the top 10 most similar chunks from the vector embeddings from this particular namespace. And if I had to show you guys, this is how the result is going to look like. There's a score, there's an ID. The ID is going to represent the number of chunks that we are talking about, and the score is going to represent the level of similarity between these three, between the query and the actual content. So 0.85, remember, cosine similarity goes from -1 to 1. So 0.85 is a very high similarity score. So let's visualize what the content is actually going to look like. And this is how the content is going to look like. It's a simple loop that I ran over the documents to get the page content. And we have our SMBO relevant content here. Another thing, like you might be asking, where is the page number? So for the page number, what you can do is you can remove the subscript for page content, and you will be getting the page number alongside the content as well. So The first chunk corresponds to page number 9 and similar. So this is how you can actually create your own vector search. The considerations that you need to take before doing this is the types of data that you are going to be having here. I was able to narrow down that it was a text search that we wanted. I think I got disconnected. Let me know if I'm audible.
Yes, Ani, you are audible.
So how long was I disconnected for?
Just for a few seconds. You can,
Okay, that's
yeah, you
oh,
can
that's
say as
good.
usual now. Yeah.
Okay. So like the second consideration that you need to take is for whether vector database is even a right fit for you or not. If you are going to be having a lot of updates to your particular directory, you might want to consider the cost that it's going to incur for you to maintain those. So if you have a lot of searches and less number of updates, vector database is definitely going to be a very easy, like a very great solution for you. But in other cases, you might want to consider all of the possibilities. The other possibilities that do exist are chunk size, which is the degree of detail or against the degree of summary that you want. Here we have a single chunk which is of 480 for 480 tokens. Maybe you want a chunk size of 200 tokens. Maybe you want a chunk size of 800 tokens. That chunk size is going to depend on the kind of case you're dealing with. Another thing is that the embedding model that you're using to convert this as well as the dimension. So I was using text ada 2, which had 1536 dimensions, which is why we use 1536 dimensions here. Similarly, you're going to, when we're talking about tokens, you're also going to be worried about costs that you will incur alongside. And a few things that you guys can play around with are the chunk sizes, the separators. Instead of using text ada, you can use any other open source embedding models which I've mentioned here. And you can, instead of just a simple vector search, you can look into how to implement semantic search to get started as well. So these are the things. One thing that I would like to point out is whenever you are creating chunks, it would be a great practice to store those chunks, because when you're going to query your the result is also going to be a vector. You're going to query a vector and you're going to be returned a vector. If you're not going to be storing the chunks that you have created, these chunks, if you're not going to be storing these chunks, you will have to convert those embeddings back into your text format, and that is going to cost you more tokens. So that is one thing that you want to look into. Now that we are done with the technical code, we can start taking questions. You can post these in the Q&A or in the comments. Are the values in the vectors sorted? They are not particularly sorted. It's more like the positions are important. Exact. So the question is from Betty Slama. Are the values in the vector sorted? They are not going to be sorted. It's more like going to be an idea of positions and which position corresponds to which value in a vector. Okay, so let's take another question. Okay, so its question is from Spencer. How does query speed compare to other DB types? Does it need a good graphics card to query very quickly? So in case you are using a model that is deployed on cloud, you will not need to use a graphics card, and it will be computed on cloud. Otherwise, you might need to opt for that, since it is a very resource intensive computation. The embedding you showed in that. Okay, so the question is from Mahesh R. The embedding you showed in the test program, was each integer an embed coordinate, or was that whole list a single embedding? Yes, Mahesh, the entire list was a single embedding, since the entire embedding was contains 1536 dimensions. So we're going to take one more questions. We can take one more question if there are any. So it's a question from Joe A. What's the difference between these vectors versus just putting your documents in language model to find table of contents? Also, are the information you fed to the LLM is protected? Is that communicated with LLM and then it's sorted in their database? So the entire argument for creating a program for your vector search is that you have an idea of the what your search solution is going to look like, and what your data looks like. The reasons we have chosen specific chunk sizes and other things is that it's not just going to be a table of contents problem for everyone. It could vary from one person to another. Um, so that's about it. I think Hubab can take over from now on. Thank
Hani, if you
you
can
for
just
the
scroll
webinar,
up,
everyone.
yeah, Hani, if you can
जी
scroll
जी
up on the chart, there are a few questions